look at this last problem here. Okay, I want to take a look at this this crank mechanism problem. Okay, and what it says here is to determine the two reactions at B. Okay, P is an unknown but necessary for static equilibrium. Okay, so we don't even know what P is either. Okay, and so we don't know that. We don't. All we know is there is a weight there of 150 pounds, though. We do know that on the thing. Okay, and so we've got to be able to figure this all out. Okay, so what I'm going to be doing to show you this, how to solve this problem, is I'm going to do this completely different than what I've done before. I'm not going to do R cross F. What I'm going to do is I'm going to show you this in three different views. I'm going to show you a top view, a side view, and another side view, looking into the X, Y, and Z. And I'm going to show you how to approach this problem without doing any cross products, a 3D problem without doing any. Thing we've got to do is we've got to draw a free body diagram. Okay, and again, I don't like drawing free body diagrams on the figure, but in this case, I think it's kind of necessary. All right, so you don't even know what's going on in A. You kind of have to make an assumption based upon. Does anybody remember what that looks like last time? What does A look like as a support? It's the one, ball and socket. That's what it is. That's what A is. So a ball and socket means you don't put any moments on it. You just put force reactions. So you're going to have an AX, you're going to have an AY, and you're going to have an AZ. That's what a ball and socket says. AX, AY, AZ. Okay? Now what else is touching ground with this thing? Obviously at point B is also touching ground. You have a bearing. Okay? Now in this case, the bearing says this. This is what's kind of a little bit different about this problem. Normally, and this kind of violates the principles here, but this is engineering, sometimes we make assumptions. Normally you look back at your charts for bearings, and you'll see two force reactions and two moment reactions. Okay? But it says here, determine the two reactions at B. To simplify, and honestly, we do this a lot. Okay, we really do this a lot with bearings. Not always, but quite frequently we do this. Is because, here's why. Notice we already have three unknowns there. We have three unknowns at A. Remember, you can only solve up to 6 unknowns. Normal bearings, you would have 4 unknowns at B. If you have 4 unknowns at B and you have 3 unknowns at A, you can't solve that. So the problem says, give me just 2 reactions at B. Well, if you're just going to have 2 reactions at B, they're going to be force reactions. Okay? Sometimes what you'll also have is it'll say, assume the bearing is balanced. Okay? If a bearing is balanced, basically, properly, it shouldn't have any moment reactions because you're not trying to tear the bearings out. Okay? The only time you have a moment reaction on B is if the bearings are trying to be ripped out or turned. That's bad. You don't want that to happen. So that's bad for your bearings. So we're going to assume, and this actually happens quite frequently, we only have 2 reactions at B, which are force reactions. Now, which way would those be? X, Y, and Z. Which 2 would be forces? X and Z, right? Because it can go in the Y. So we're going to have a BX and a BZ. Okay? Because remember, we can only have up to 6 unknowns, and I already got 5. What's my last unknown? It tells me in the problem. P. Yeah, exactly. Hey, P. P is an unknown. Okay? All right, the only last thing is don't forget about the 150-pound force. I'll draw it here just explicitly so I don't forget about that 150-pound ball or whatever. That obviously, if you don't have that force P there, okay, then the ball will want to spin, will want to drop. It will spin, and the thing will start spinning out of control, right? Okay, so you have to have somebody holding it back. You let it go, the things just start spinning. Okay. All right. What I want to do, this is a free body diagram. It's got all our forces. Remember, we can only have up to 6 unknowns. We have 6 unknowns here. Okay? Bx, Bz, Ax, Ay, Az, and P. Okay? So what I want to do now is I kind of want to do this differently. I want to give you this in 3 different views. So instead of doing R cross F, because this is a 3D problem, and by the way, you certainly could do R cross F. Okay, there's nothing wrong. It's not like you can't do it a certain way here. But we're going to do it a different way. So I don't care which view we start with. I decided, let's start with the ZY view. So let's pretend you are looking at this picture. You're looking straight at it from the x-axis. When you're looking straight at it from the x-axis, you do not see x-direction forces because they're coming straight at you. Okay? It's like they look like a dot to you. Okay? Okay? I mean, it's like, if you have something that's infinitely small and I look straight at it, you don't see it really, right? If it's just really tiny, right? If you look at the side view, you go, oh yeah, I see it. But if it's, you don't see it straight at you, okay? So you don't look at x-direction forces. You only see y's and z's. So let me draw that picture for you. What we have here, it looks like this. Here's my y-axis. Here's my z-axis. If you're looking straight at it from the x, okay? Now, what does this thing look like? Well, it looks kind of like this. If I draw it, it's going to look like this. You're going to see this. Then you're going to see the spool, right? Okay. Then you're going to see this. So it kind of comes down like that, right? Kind of looks like that, just to kind of give you a picture of it. If you look at it straight like that, okay? I didn't draw the bearing, but I think you get the idea. Okay. So remember, when you look into the x-axis, you don't see x-direction forces. All you see are, there's a force here, AY. There's a force here, AZ. There's a force about, let's say about right here, BZ. There's a force, I guess sort of right around here, 150 pounds, right? And is there any other forces I have forgotten, or is that it? Remember, you don't see x-direction forces, so you don't write AX or BX. Because essentially they would be just dots in this picture, because they're coming right out of the page. Okay? What's that? Okay. So, taking a look at just this picture, is there any of those 3 forces you can solve, and how? If you know things about moments, you start going, maybe I could use a moment to solve one of those. Yeah. When in doubt, moment about A, right? Yeah. Moment about A, right? Because, look, it has A, Y, and AZ. So the only unknown force that has moment about A is BZ. This is going to be quick. We can solve for BZ real fast, okay? Because look at this. What's the distance between the 150-pound force and A? It sure looks to me like the picture showing this is 2 feet, right? And what's the distance between the 150-pound force and B? The picture sure looks to me like another 2 feet. All right? So this is really easy. If you do this in this picture, you sum the moments about A equals 0, counterclockwise positive. What you've got is this, minus 150 pounds times 2 feet plus, plus BZ times 4 feet equals 0. That's easy. BZ is equal to 75 pounds. So very quickly, I have been able to identify one of the reaction forces. Okay, anybody have any other thoughts I can do with this picture? Yeah, why not, right? What do you do to find AZ? You could sum moments about B, certainly, you're right. But even easier would be to just sum forces in the Y. I mean, you're right. I mean, yeah, you probably thought that first and thought, well, I better go with the moment equation because it sounds better. Right? Okay, yeah. It's even easier to just sum forces in the Y, sorry, in the Z, in this case, in the Z. Sum forces in the Z. So let's sum forces in the Z equals 0. That's up is positive. That's easy, right? This is AZ plus BZ minus 150 equals 0, but I already know what BZ is. BZ is 75. So that's kind of easy. AZ is also 75. Okay. Lastly, can I get AY? No, don't make it that complicated. Third graders may be able to tell me this. No, I'm not insulting your intelligence, but I'm like, this is that simple. AY is 0! Yeah, I'm not insulting your intelligence, but I'm saying that it's that simple. Because that's the only force, right? Some forces in the y direction equals 0. You only have one force, therefore it must be 0. Okay? I'm just trying to tell you it's easy. Some force in y equals 0. You only have one force in the y, therefore it must equal 0. Now that hasn't solved everything, but it's a good start. We got 3 of them. We need to get 6, and I got 3. So now what do? Change views. Draw another picture. Yeah. It doesn't matter which one we do. I mean, I certainly, usually I don't know which picture to do right away. I mean, I don't necessarily know, oh, it's obvious I should do this one or whatever. A lot of times I don't know which one. What I'm going to do this time is let's do the XZ view, okay? Let's look into the y-axis, okay? And look at it from the side now, okay? Looking into the y-axis and looking at the side, here's what this is going to look like. It's a little bit messy, but let's do it. We can do it. Here's x, here's z. Here's x, here's z. Because we're looking at the y-axis, so the x goes left and the z goes up. Now, in this case, we see a lot of things on top of each other because what you see looks like this. As far as the actual object here, what you see is you've got the inner tube, you've got the outer tube like this, and then you see the handle coming down, right? And then you see the bottom of the handle there like that, right? That's what you see, right? Because you're seeing the side view here, okay? So you don't see much looking into the y-axis because most of the thing is parallel with the y-axis. But you do see a lot of forces. Let me start writing the forces you see. In fact, you see AZ and BZ both going like this. Here's AZ and here's BZ. I'm going to draw them like this. They're really on top of each other, but they look like that. Because that's what you're going to see looking into the y-axis, AZ and BZ, just like that. And you're also going to see AX and BX like this. They're really on top of each other, but it's hard to draw them on top of each other. Okay? Now the 150-pound force, you do see pretty easily. It's out here. That weight force, because if you look at the picture very carefully, you'll see that spool has a radius of about 1/2 foot. So that 150-pound force is actually 1/2 foot here out from it's 1/2 foot in the positive x direction. right? It's a half a foot in the x. It's not directly at A. It's a half a foot to the left because of the spool radius. Okay? And then what's the last thing you see? The force P. The force P you see like this, and I'm not going to probably draw it exactly to scale because it's going to be a little longer, but I'll draw it like down here. I didn't really draw this to scale. But the force P is down here. And if you look at this, force P is 1 foot below. It's a foot below down in the z-axis because that crank goes down 1 foot. You see that? So, I can easily solve for P. Anybody know how? So a moment about, yeah, this point here, this point in the center here. I'll call it A, but you really, I mean, it's really A and B. If you call this point here, it's really A comma B, right? Because you can't see the difference between A and B looking into the y-axis, right? I'll just call it A, okay? So if you do sum of the moments about A equals 0, this is pretty easy. You've got a 150-pound force, which has a half a foot distance to A. That's a positive moment. Minus P times 1 foot equals 0. Therefore, P is also equal to 75 pounds. Okay? All right. By the way, you can also solve looking at this picture. If you look at this picture, sum of the forces in the y direction is equal to, sum of the forces in the z direction. Sum of the forces in the z direction is equal to 0. You have AZ plus BZ minus 150 pounds equals to 0. Oh, we already got that. I'm sorry. We already got that one. We don't need that. Sorry. We don't need that because we already got both those. That's just obvious, right? They're both 75. Oh, sorry. We didn't need that one. Sorry. Didn't need that. We already solved AZ and BZ. How about AX and BX? Can we solve that? Well, we really can't, right? Because we can write this. Sum of the forces in the x direction equals 0. And we can say AX plus BX plus P equals 0. And we know P is 75 pounds. But that doesn't help us solve AX or BX, right? So what do you think I have to do to solve AX or BX? Draw the other picture. Okay? All right? Now we're out of time here. But what I will say is I will leave this on your own as a practice, okay? And I will tell you, if you draw the other picture, you will find BX is equal to minus 112.5 pounds, and AX is equal to 37.5 pounds. The negative means that I just drew it wrong in my picture. Doesn't mean anything else. No big deal. So I challenge you to draw the other view, which is the XY view, and see if you can solve those two. We don't have time anymore to do it now. I'll do a quiz.